All right. Well, thank you all for, thank you very much for the invitation to come. Um, uh, uh, as Dr. Uden mentioned, I do have roots here. Overall, one of the things that I want to introduce you guys to is a molten salt reactor that is going to be built in Abilene, Texas, in the next several years. So in this first slide, there is a picture of timeline at the top, and in the bottom left corner, there is a ACU in the state of Texas. That ACU is where the university is. It's about an hour and a half drive west of Dallas, about 3 hours north of Austin. There is not much else there other than oil derricks and farms. It is a university town. There are 3 different colleges there. In total, it's only about 15,000 students, though. ACU has 5,000 entirely undergrad students. And so this really came about from someone who is on the board of directors at ACU that was looking at energy in Texas and what should happen in the future. And when a large commission in the state of Texas got together to investigate what would energy look like in Texas if it went carbon free, the answer came back: nuclear is 100% required. There is no way the state of Texas can have an economy without nuclear energy. And especially a huge need for high temperature production, because there are so many chemical and industrial facilities. I'm going to pop on the participant list here. I just muted Zach. All right. Sorry, Zach. So they basically said, looking at the energy needs in Texas, there needs to be something that is generating high temperature source of energy. There's so much stuff that oil and natural gas burn to allow the industry to work, and nuclear is really the only answer. And so he went back to his hometown and was talking with people there at the university and was like, man, I really think that, something should happen with this. And so they started writing proposals to do molten salt research on flow loops and chemistry and heat transfer. And really through the 2010s, they just started getting more and more capability and understanding. And they said the next step is to build a nuclear reactor, but we're way too small to do that on our own. So they reached out to the major universities in Texas, University of Texas and Texas A&M, and said, we want to do this. Do you guys want to help? And so we said, yeah, that sounds great. In 2020, the project was officially started. The next lab is the laboratory at ACU for salt research. The Nextra consortium includes Texas A&M, the private company that is funding this. ACU and a faculty at University of Texas left for Georgia Tech, so we said we'll let him stay involved also. And so it's Texas A&M, ACU, the private company, and Georgia Tech working together on this. The preliminary safety analysis report was submitted in August to the NRC. They reviewed it. They said it is complete. It has everything we need to understand, is this going to be safe or not? And so they are currently reviewing it and have said that they anticipate in about a year from now, they will tell us yes or no on you can construct this reactor. And so I'm going to walk through a little bit about what's going on with this. But first, I'm going to give you an intro more to UT nuclear program and sort of my research and what people in my group do. So the overall outline, looking at nuclear at UT, what computational nuclear engineering at UT looks like, design and licensing of this molten salt research reactor, what it has entailed, and looking at sort of ModSim R&D for this and future molten salt reactors. So there are 4 tenure track faculty, plus Dale Klein, who is Associate Vice Chancellor. We are in the process of hiring one more faculty as Dale Klein is starting to retire, but we span a breadth of experimental to computational work. 2 new research engineers have been hired to join in on this project in the past year. Ben Collins was 10 years at Oak Ridge National Lab working with me on modeling simulation for light water reactors, and Andre Chavala has about 10 years experience doing molten salt reactor design and analysis. Derek Haas has been doing a whole lot of the facility design. What experimental systems do you have? How are you going to establish your operations and your monitoring? And Bill Charlton has provided a whole lot of guidance on the execution of the safety requirements and reactor oversight committee and that kind of thing. My work overall in the nuclear program, Mitch Pryor is also a research engineer who focuses on nuclear robotics and does a whole lot of work with machine learning and Army Future Command type of research. So overall, we have quite a few connections inside of the nuclear engineering program. The nuclear engineering program is housed within the mechanical engineering department. It's 75 to 80 faculty. It has a broad range of acoustics materials, and so nuclear is just a small piece of it. But it is intentional about establishing multidisciplinary research. The reason all of these fields, which in many places are separate departments, the reason they're all housed in mechanical engineering is to intentionally foster multidisciplinary research. We have a 1.1 megawatt trigger reactor. We have neutron generator and tons of labs for radiation and chemistry that as a computational person, I am not allowed it. But we do work with the Odin Institute for Computational Engineering and Sciences. This is a separate degree program, and it intentionally integrates math, computer science, numerical analysis, and engineering, and brings together people who are doing computational high-performance computing R&D to begin to communicate, interact. So the people that are modeling blood flow through veins can work with the people that are modeling drone flight patterns and nuclear reactors. We also have the Texas Advanced Computing Center, which has the biggest, most powerful university supercomputer. It has an export control enclave, so we have all of our nuclear codes running on it. One of the big computers on there is state of Texas funded, so we don't have to worry about is this okay for nuclear codes or competing for time, because the state of Texas said we're going to buy you a supercomputer. They're already planning the next supercomputer to be built, which is going to be an exascale computing computer, again funded by the state of Texas. There's also the Texas Materials Institute on the UT campus. Other people who do experimental work have SEMs and TEMs and other toys that I don't get near. And then there's the Dell Medical School. That is a relatively new school. I think it started in about 2015. And we have collaborations with them on medical isotope production. In general, we have about 40 undergraduates in mostly mechanical engineering and physics. So there is a concentration area within ME in nuclear radiation engineering. And in physics, there is a radiation physics concentration. We have about 63 graduate students, which means we're about 12 grad students per faculty. We're graduating in the range of 11 degrees per year, about 2 per faculty. Overall, about 800,000 per faculty in research expenditures, with the big projects being the nuclear robotics for military, the medical isotope production, and the design and licensing of this molten salt research reactor with ACU that I'll talk about. So where did I come from? I was grew up till I was 9 in Kankakee, about an hour north of here. I still have family in Farmer City and Leroy and Bloomington. Then moved to Austin, Texas, and was there all the way through high school. Went to MIT. In high school, I decided nuclear energy is the right thing. It may not be popular now, but it's obviously inherently the right solution that we need to have. So I was all about nuclear engineering. And last time I was here on this campus was when I was a high school junior looking at where do I want to go for college. So it's good to be back. I got my bachelor's in nuclear engineering in '99 from MIT, looking at reactor optimization, and I went to Texas A&M in part because there was a girl that I was dating who was living in Texas. And it turned out to be a great program, and I loved it. I did nuclear reactor accident analysis for my master's, and then switched for my PhD to radiation transport modeling. And then I got a job at Oak Ridge. And so at Oak Ridge for 15 years, I was research scientist up to group leader. And one of the projects that I was leading, we're still working with some of that software. It's called the Castle program. That was a collaboration between 4 national labs, industry, and universities. While at Oak Ridge, I also was working with University of Tennessee as adjunct and joint faculty, teaching some classes, advising some students. And when Oak Ridge wanted me to start doing leadership training with their little internal education programs, I said, rather than take your little Oak Ridge specific management training, why don't you guys just pay for me to get a MBA? And so I did an online MBA while working full time, and which paid dividends when COVID hit, and everyone was suddenly doing online training and education. I was like, I know a little bit of your pain because I was experiencing it on my own. But then in 2018, 2019, I started looking around, are there other options? And just landed in a great spot going to University of Texas. And so I am in my 4th year there as both associate professor in nuclear radiation engineering. I have a affiliate faculty appointment with the Odin Institute, and I have a joint faculty appointment with Oak Ridge National Laboratory because they said, why don't we create Oak Ridge West in Austin, and you guys just start doing all kinds of Oak Ridge National Lab related things, because we need a pipeline of great people coming in here. So I'm going to move the Zoom big thing, cover up that logo. It's not as interesting. Oh, you guys can't, maybe the people online see it, I'm not sure. So you can, I know you can't see it up here, but on the Zoom. So on Vera is the virtual environment for reactor applications. This was a 10-year project at Oak Ridge National Lab where we were looking to address some of the limiting problems in the light water reactor industry by using advanced simulation. In doing so, we coupled full 3D radiation transport code called IMPACT with a full modeling every single channel between fuel rods in the reactor, thermal fluids transient code called CTF, with isotopic depletion, depleting radial rings of every single fuel pin with about 100 axial regions. So millions of spatial regions modeling every single isotope to really improve the understanding of the power distribution, the temperature distributions, and feeding into fuel performance. So in this project is when we were really striving to begin to couple the different physics at a fundamentally different level. So how I felt when I started working at Oak Ridge after a couple of years, I said that the people that are going to lead this field in 15, 20 years are the people that are able to take the individual physics, because back then it was like you are a radiation transport person, and over here there is a thermal hydraulics person, and over here there's a fuel performance person, and they just kind of chuck things over the fence. You know, here's the power distribution, here's the temperature distribution, and each of you worked in your little box with your own tools to try to design things. And said the only way we are really going to advance is if we start to create tools that integrate all of these physics that allow for one input and a group of reactor engineers to sit down and look at one input, one design together, look at one result and discuss what should be changed. And so with this castle project, by developing Vera, we were able to do that at a dramatically higher resolution than the industry was used to seeing. We were also able to start putting together some more algorithms for multiphysics and multiscale coupling. If this one starts playing, there we go. I clicked it. So the shift code is a continuous energy Monte Carlo code. And one of the challenges is, what does vessel fluence look like? And so we started to say, not only can we look at in-core of coupling deterministic transport with fluid flow, but we can also feed that to power distribution to Monte Carlo code to be able to do what is vessel fluence. And with the vessel fluence, you can start to answer questions of, as the vessel ages, if there's an accident and large temperature changes, what's the impact and likelihood of embrittlement? And so starting to push forward on coupling different scales, different fidelity software. We also started coupling in fuel performance. So that CTF has a fuel model, but it isn't really modeling all of the physics and fuel performance. And so when we had the fully coupled impact CTF origin Bison, this was having full fidelity 3D radiation transport, modeling flow through every one of these channels, and modeling the nuclear fuel performance for every single fuel rod in the reactor. So we had 50,000 individual Bisons running all at the same time to model and understand exactly what was happening inside of the fuel at that level of fidelity. So it really opened up a whole lot of doors. And one of the challenge problems was folding in surface chemistry. So crud will build up on the outside of these fuel rods. And so we went from doing, all of these codes coupled to now we're trying to do surface chemistry. And this was really the first time that I ran into, we don't have enough data to be able to get the answer right. It is difficult to try to figure out junk that collects on the outside of individual fuel rods that is due to the turbulent flow patterns and the subcooled nucleate boiling on the outside of these fuel rods. And there isn't enough experimental data to really understand that distribution, understand where the modeling and simulation fails. And so it was as we were nearing the end of Castle, I said, I think we've started to realize this vision of multi-physics coupled codes, but the next step, the next advancement, and it's a challenge I pose to all of you, the people that are leading in modeling and simulation, leading in nuclear energy applications 20 years from now, are the people that are going to be integrating simulation and experiments. We can't just say, let's continue to refine and perfect the simulations. We need to actually start pulling data real time, which means we need to start building nuclear facilities. Which brings me to building some, oh, nope, I'm not there yet. So other things in general, looking at using high performance computing for single physics codes to generate numerical benchmarks, looking at model reduction of data for capacity computing, to understand how we can have these big supercomputers with really great high fidelity single physics codes like Monte Carlo codes, but be able to use that to create medium fidelity codes that are actually usable and useful for engineering analysis. Looking at doing single physics codes integrated together with more moderate computing power to do multi-physics analysis like Vera, but on a lot of different applications to really understand where the errors come from, where we need to invest in putting new improved modeling capability, improved data generation to really figure out what we need to do to improve our software. And then lastly, as I mentioned, starting to integrate advanced simulation experiments to leverage the growth that we see in machine learning, to start really developing digital twins, to develop and qualify predictive software. We need to allow for innovation. So one of the things that will enable this is a brand new advanced nuclear reactor. So the molten salt reactor, UT is involved in this. My sort of computational role, my group's computational role is neutronics analysis for the design and licensing piece, developing advanced computing capabilities for optimization and multiphysics analysis, and looking at design and analysis of experiments that will enable the licensing, and developing some digital twin technologies. If you're not familiar with digital twins, and I know I have less time, so I need to pay attention to that. All right. If you're not familiar with digital twin technologies, it is the idea of you have an experiment or a facility that is generating data real time. You are gathering, collecting, organizing that data real time, and you have a computer code that is comparing results with that data to learn how to operate or to improve that software real time. You might also have additional codes that are off to the side that are occasionally taking snapshots of that data to improve even higher fidelity codes. In the existing suite of nuclear reactors, instrumentation is all about safety analysis. Is this safe? Is it not? When do we need to throw control rods in? When do we need to shut down? If we are developing a whole new suite of advanced nuclear reactors, we need to think of instrumentation fundamentally differently. We need to think of instrumentation as, let's gather as much information as we can in real time. Every time something changes, we need to be gathering all of that data, and we need to be able to have software that is modeling all the physics that's going on, so we can understand where is the software missing the mark. Because if we can develop software that really is predictive, without just hand-tuned calibration, but actually has the correct physics folded in, and every time the reactor changes, we're able to predict what happens before it happens, then we can start to go to the NRC and say, we want to innovate. We want new ideas, new changes to these reactor designs in a way that before they would say, you want to change something, show me your decades of experiments specifically for this change. And here, if we start to instrument reactors differently, then every reactor that's operating can start to provide more of a knowledge basis for this, especially if we have a university research reactor where you're going to be starting up and shutting down, especially in the first few years of operation when we have no idea what's coming. And so those first few years, weeks, days, is going to be tremendous data, because everything is new. Everything is brand new data points that we have never had before, or in the case of a molten salt reactor, we technically haven't had since the 60s, but their simulation, their instrumentation capability, all of that was so different back then that it is just dramatically better information we can provide. I'm going to skip this. So in general, this is from a presentation from Idaho National Lab talking about the new reactors that are going to be built that they are associated with over the next decade. Hopefully you guys have seen this or a similar presentation. It is a great, awesome, exciting time of what's coming in the future in nuclear. And I hope all of these get built. But we are hoping that the University of Illinois has a reactor sometime on this list, and it's not here yet. And we're hoping that Abilene Christian also has a reactor that gets added to this list at some point. There are going to be a lot of challenges with regard to building all of these reactors, but all of these reactors, all of these experiments can all start providing more and more data that is used for simulation codes to compare with, to understand where are they lacking, where do they need to improve. Is it the physics? Is it the data that feeds into the codes? Where's the problem? What do we need to do about it? So let's see. So one question that we often get is, why did you choose a molten salt reactor? Like, isn't that kind of the hardest one to start from? Yes. So in general, it is proven, it's safe. It has been demonstrated to be able to be operated cleanly and efficiently. It is very multifunctional. It is providing high temperature salt with fission products in it. If you want to use that heat for something, there's a variety of things you can use it for. And that salt, if you want to start doing chemical processing of the salt, it's going to have, you know, cool fission products. It's going to have some tritium in there. It's going to have some plutonium and other things. So there's a variety of things that in theory could be done with a molten salt reactor. It's scalable, it's carbon free. That molten salt reactor that operated in the 60s operated great. It was at 5 years of excellent operation. And so we know we could go to the NRC and say, there's proof that this reactor could be built. So we're going to build one like it. But now we're going to be able to generate modern data. So why a university research reactor? Why not just build a commercial one, a test one? A lot of those on that list of INL are straight from a commercial vendor to a brand new reactor. The reality is the last MSR operated 50 years ago. There's a lot of research that needs to happen. The fuel and waste issues are dramatically simplified with a university research reactor. DOE Office of Nuclear Energy has provided ACU with a letter that says, if you build this reactor, we will welcome you as part of the Research Reactor Initiative program. In that program, DOE provides the fuel. They own the fuel for its lifetime while it's operating, and they own the fuel afterwards. It funds the transportation of the fresh fuel and funds the transportation of the spent fuel away from it. The licensing is also dramatically simplified. By definition, university research reactors better be extremely safe. You're occasionally sitting down and training university students on how to run the reactor. If it's sensitive, then that's not a good university research reactor design. So there is a whole lot of significant inherent safety built in. In general, the power reactors are designed to operate much closer to sort of operating in safety limits to get as much power as they can. This is a fundamentally different purpose for operation and design. There is a whole lot of support for this reactor. The building that the reactor is going to be housed in, the city of Abilene has paid $5 million in order to build this building. The state of Texas, it was introduced to the House and the Senate in the state of Texas. The congressional leaders there learned about it, and both the House and the Senate wrote resolutions last year saying, we know about this reactor, we're in full support of it, and we want it to happen. And then Department of Energy and NRC have been supportive of this reactor all along. So multiple levels of government engaged and aware. Key goals for this is to demonstrate that this kind of reactor can be licensed, even if it's just a research reactor. This hasn't ever been licensed by the NRC. And we need to establish suppliers for all the components. There are construction and supply chains that have traditionally plagued traditional advanced reactors. A lot of the modern advanced reactor design companies are just doing phenomenal work crushing the what is our supply chain process. And in this, we're not going to figure out the long-term supply chain because the first reactor we build is probably not the ideal molten salt reactor. The first reactor is really just demonstrating that this can be done. So we aren't necessarily working all of the details out for supply chain, but we're getting at least some of these in place. Really the main thing is we want to generate this operational data. We need to figure out how you manage molten salt chemistry. We need to qualify nuclear software. We need to understand how you have material accountability, how you make sure that a little bit of salt with uranium and plutonium in it doesn't walk out the building. And then there are just, quite frankly, a lot of things that we won't really know till this thing is operating. It's going to be fascinating to see what things did we discover that it was like, oh, what is that? What are we going to do about it? There are a lot of unknowns. And if you're trying to design the perfect reactor, those things are crushing you and killing you. But if you're designing a research reactor, these are great new research problems. And so it really sort of opens that door for let's figure out what things that in the 60s they ran into and they got an engineering fix for, and it has been forgotten. So this Science and Engineering Research Center, the CERC building, is the picture at the top. At the bottom, the trench is there. The walls are about to be stood up in this picture. This was from October. And so those walls are up. The roof is on the building. So that building is being constructed. It is officially a general purpose facility, but it has a large trench that is 24 meters long, 7.5 meters tall, 4.5 meters wide. In that trench, you could theoretically house 3 of these research reactors. The desire is not just to build one research reactor to demonstrate it can be done, and then start building the next one and drop it in the trench alongside of it, because this first one is, let's show that we can do this and let's get some data. The second one needs to be a little bit closer towards what you actually might want to build in commercial, but even then, you're generating more data, more understanding of these systems, these physics that are associated with it. So lots of this design is built on shared concepts with the MSRE. It is uranium, lithium fluoride, beryllium fluoride fuel salt. It is a loop design. It has graphite moderator. There's a big drain tank underneath it. So when you need to shut down, you just drain it. You have it stuck inside of a trench for most of your radiation protection. And the MSRE operated for 5 years. So we said, we're going to only operate for 5 years. This isn't a reactor like most of the reactors you see today, where they're at 60 years and they're saying, can I get to an 80-year lifespan? This is an experiment. It's designed 5 years of operation, because after 5 years of operation, hopefully there's another reactor. We can pull the fuel salt out, maybe put it in the other reactor, and then take that reactor out and cut it up and do destructive analysis and learn what corroded. Where did salt get stuck? Where did the tritium go? What did we learn by chopping these pieces up and looking at it? But we've also simplified a whole lot of things from the MSRE, dropped the enrichment down to LEU, dropped it down by an order of magnitude in power. Stainless steel 316, it's a whole lot easier. It's already nuclear qualified compared to Hastelloy. There is no off gas system required. There is no filtering of solid particulates required. And we have 50 years of technology advancement on things like sensors and instrumentation. All of these reactor components are going to be sitting inside of the trench. So this very first one, we're going to use a big chunk of the trench with a reactor in the middle, some fuel storage on one side, the secondary loop on the other side. All of that primary loop is going to be inside of a sealed container. So if salt spills out of the reactor core, it is going to take a while for it to get out of that sealed container, and shouldn't even ever get outside of that sealed container. So that reactor enclosure, there is this drain tank underneath it. This is the actual shape of the drain tank, unlike the last picture. So a scram is fundamentally different than most reactors. Most of the time a scram means we drop the control rods in. Here the scram just says, let's just equalize the pressure in the drain tank compared to the pressure above the reactor, and all of the salt will just drain into the drain tank. That decay heat down in the drain tank will be passively removed naturally, because there isn't as much insulation around that piece. All of these primary components are inside of a steel enclosure, and it is subatmospheric pressure. So if there's a salt spill accident, it all stays inside of this enclosure. And that enclosure is down inside of the trench that has a roof over top of it. And so it's inside for shielding to protect people around it and minimize the radiation levels throughout the facility. It really is a mini version of the molten salt reactor experiment. These are not perfect pictures of what this reactor would look like, but in general, it has the same general structure concept of flow channels in orange through graphite blocks that are shown in blue. and low power, low number of years of operation. So for modeling simulation, there's suites of types of codes that we use. There's lots of single physics codes that are out there. Your CFD, your Monte Carlo. These are high resolution, very few approximations. In general, they tend to be very easy to validate because you can set up an experiment just for this single physics. But oftentimes they prove to be very difficult to do coupled physics analysis. Then you have almost on the opposite spectrum, your system dynamics codes. These are relatively low resolution multiphysics. So in LWR world, Trace and Relap 5, 3D, Melcore. In the advanced reactor world, there is the SAM code from Argonne and Idaho working together. And so in general, these have relatively low resolution multiphysics. They often model the reactor as a zero-dimensional point in space, but they can do all kinds of transient analysis. They have things like control rods drop in, how much do the pumps slowly creep down in speed. If you have operating data, they're very easy to calibrate. You have all of these, knobs for how slowly does the pump grind down, how do kinetics work. And so if you have enough operating data, you can make that code get a pretty good answer for integral type of quantities. But they prove to be very difficult to make predictive because in making a simplified one-dimensional flow in a zero-dimensional reactor, you just fold so much stuff in there that it really can't predict what would happen if. So in the safety for the current reactor, these system dynamics codes coupled with some single physics codes are perfectly sufficient to be able to say, can this operate safely? Yes. And that's in part because it is such low power. There is only a 30-degree temperature difference from inlet to exit. And so it's 600 degrees in and 630 flow out. So there isn't huge temperature gradients. Power distributions are relatively flat and smooth and predictable and insensitive to system changes. But if we want to move to a world where we are really predicting things, then we have to have coupled software. We can either use integrated tools that couple individual single physics codes, or we can use general multi-physics tools. There are benefits and challenges to each of them. If you have like Vera, you have I have this great code here and this great code here, and I want them to work together. You suddenly have a software engineering problem, and it's not nuclear engineers, it is software engineers that go, how do I make this work? But validation is very logical because you can test this one code really well and this code, and then you put them together and you just have to make sure that the interface between them works well. The general purpose multi-physics ones have a lot of benefit also. They're designed to be parallel, they're designed to be coupled, they're designed to work together. But a lot of times they tend to have limited native capability. They're often a finite element code, and you're like, oh, well, the structural mechanics piece is easy because continuous finite elements are great for structural mechanics. But fluid flow and radiation transport tends to be difficult. And so it's well, maybe we could just use diffusion. Diffusion will work for radiation transport. It fits well for my code. And so often you're making algorithmic choices to work with your code package. Whereas a coupled single physics, you say, what's the right method for this single physics? But then you have to figure out how to get the things work together. So each one kind of has its own challenge, and we don't know what's going to win in the future. But one of the challenges with multiphysics is without our operating reactor, we wouldn't even know which one was right in the first place. Hey, congratulations, you have a code that does multiphysics, and you do too. Which one's right? I don't know. We can, claim my algorithm's better, my method's better, but until we have data, we don't really know which one it is. So we sat down, let me check out the time, make sure I'm not leaving time for questions at all, since we got started late. Okay, so we went through and took a look. You guys on your own, you can read faster than I can talk. We looked at what are the requirements for system code selection. There are real requirements for fundamentally what they have to do, and then sort of softer requirements for our team. How is this going to work for us? From that, we decided the system code we use was going to be Relap 5 3D. It had the physics we needed. It was missing some of the pieces, and so we put in a game voucher to work with INL. And one of my students said, okay, what do we need to do to change inside a relap to make it be able to model flowing fuel salt, because it was never made for that. An A&M student said, how do we get the right properties in there to model different salts? And it worked, and it's sufficient. It's not necessarily ideal for the long term, but it meets the requirements. It allows us to be able to evaluate, is this safe? Can this work? So in the preliminary safety analysis report that you guys can all get access to, because this is fully publicly available on the NRC's website, you can take a look at chapter 13 of the SAR, and you can look at all the different reactor analyses that were done, looking at things like a salt spill accident, a maximum hypothetical accident, or cooling anomalies, or fuel handling issues. And so looking at a whole variety of these accidents, Relap was sufficient to be able to go through and take a look at some of these. In general, things like what is the limiting reactivity insertion accident? We know that there's a material failure limit is up about 500 or 850. So a safety limit says, let's make sure we're not above 810. And our normal operating limit is maybe 50. But then, in a really bad reactivity insertion accident, how hot can you get? The fuel salt's only going to get to 730. We have a whole lot of room before we get to any type of critical limit. And that's what you want inside of a university research reactor, because it's a really first of a kind plant. You need lots of that margin for safety. So we want to design this thing so that it can be so passively safe that students can operate it. I still wouldn't trust me with it, but some trained students would be a fine idea. As we look towards the future, we know just on the system modeling piece by itself, we need to account for more of the physics. Relap isn't. We need to have more higher resolution software that is informing each of these lower fidelity physics. We need better QA. We need better numerical analysis. We need experiments, separate effects, and integral effects. We need to be able to calibrate it from the operating data. We need to have optimization and uncertainty quantification. We need tools for engineers to use it, like what is the actual numbers I need? What is the visualization to look at it? And we need it integrated and coupled with that scientific surveillance layer, all of the instrumentation, all the real-time data that's generated. And I'm going to end with that. Though I'll throw one more plug in. I have a posting to work with me on ModSim for this project, for a postdoc or for a research scientist. And grad school, certainly welcome to students that want to move to warmer climate. Would love to collaborate, with you guys and the things that are going on here. I've heard a bunch of stuff about what you guys are already doing with Moltres and your molten salt reactor stuff that I'm looking forward to hopefully building some collaborations here. And I'm free for any questions.
Right, questions for the knowledge.
Sure.
Thanks for your presentation. Curious about the hierarchy validation you mentioned in one of the slides. So can you elaborate that more? What's the benefit?
What's the benefit? So I'll give you the example with Cobra TF. So Cobra TF is a subchannel flow code. And for light water reactors, you can set up, a simple single bundle flow loop. So they have a whole lot of 5x5 fuel pins that they have instrumented within individual channels to understand the flow and the temperature, and they can electrically heat those 5 fuel rods, and they'll run a whole bunch of experiments, steady state and transient. And so they can build in this little 5x5 template, just a huge range of, liquid, pure vapor, boiling, coming in 2-phase and not being heated. And they can just create a suite of what are effectively single physics, thermal hydraulic experimental data. And you can use that code and you can look at, okay, what is the cross flow? Because in that Cobra model, you'd say, you know, some flows from between these regions. If you model it in CFD, the CFD will just naturally let the flow move between them. So the CFD you can use to say, is it right? Is it accurate? How do I do turbulence? How do I do mixing? How do I do meshing? And then from the CFD, you can look at what cross flow is happening between at different temperatures and powers and void fractions. And how do I create a simplified model inside of Cobra to account for that and make it accurate? And I can do all of that with just pure flow experiments. And then maybe I can move on and say, okay, maybe I want to do a full 17 by 17, but I don't have nearly as much detail. And so I get more detail, still electrically heated rods. And then when you start the reactor up, you're going to have the full suite of all of these rods in there, but you can still do flow testing. You aren't going to electrically heat it, but you can do a whole lot of flow testing to change the temperature of your system, to change the speed of the flow and be able to compare. And so all of that is sort of a hierarchy building more and more fidelity of just the thermal fluids. On the radiation transport, you can say, let me do a critical experiment and do a variety of these critical experiments and all, you know, isothermal temperatures. When you're when you're starting the reactor up, you put in control rods, you're moving banks of control rods up and down, you're having different isothermal temperatures, and all of that is data for the neutronics. And so the neutronics you could look at, because it's independent since isothermal, it's really independent of that flow. And so you can validate the neutronics, you can validate the thermal fluids, and each of them you're sort of progressively evaluating with more and more separate effects experiments before you start doing integral effects, where you say, okay, let me have some low power. And now I have a neutronics coupled with thermal hydraulics, and I need to see how accurate is this. That makes sense? Any other questions?
So I've got one question. You showed the power as a function of time and the temperature.
Mhm.
The power showed, I mean, it goes from 1 megawatt to almost like 9 megawatts, and the time scale is in seconds.
Yes.
So is that what happens?
So this is basically so we have two basically limiting accidents. The limiting reactivity insertion accident is how many things could we turn off to make this as bad as it could possibly be. And so in this, the initiating thing was the pumping the fuel salt stopped and it coasted to a shutdown. That's 70 PCM reactivity insertion. We said, you know, there is going to be some gas, xenon gas inside of the coolant. What if we pretended that the xenon gas magically just disappeared from the reactor? I physically no idea how that could happen, but if it did, that'd be a 400 PCM burst of reactivity. If the gas itself, independent of the xenon, the gas itself leaves the reactor. If there were a whole bunch of bubbles, it was 3% void, and now all those voids immediately just disappear. The fuel would fill the void, so you'd have more reactor in. That's another, I guess that one's 400. The other one was 120 PCM. If the control rods also accidentally had been inserted and they withdrew themselves at the same time, 190 PCM. And now if there's no scrams, there's no draining of the fuel salt. So if all of these things happened, it was something like almost $1 of reactivity. And so going through, they put some, reasonable time frames for each of these. So they weren't necessarily all instantaneous. And it went up to, 9 megawatts. So no, it's not a realistic type of accident. The other one we talked about was the sort of maximum hypothetical accident. And that one we said, what if the reactor was operating at full power and then there was just a major dump of all the salt into that bottom of that vessel?
Going back to the previous one.
Yep.
It reached 9. So what brings it down?
What brings that temperature down?
Power.
so the reactivity is gonna shut off because temperature goes up.
That's the only thing that's keeping.
Temperature is shutting it down. Is a really big Doppler. So in an LWR, you have isothermal temperature coefficient of -2 ppm per degree K. In this, it's -12. So 6 times as strong Doppler feedback. It's shut down. But it is that heat removal. You know, you have some insulation around this thing, but as it heats up, even if you lose some cooling, it's going to be dumping a whole lot to that outside system.
Any other questions? Thank you very much. Sorry about the glitch.